Hi, and welcome to my third video in a quick little series about plotting sensor calibration plots. In the last two videos, we discussed what it looks like to plot an ideal line, which we have here, and we talked about null error. This video, we're going to talk about sensitivity error. So just as a recap, we have a pressure sensor. This is a differential pressure sensor that takes in a difference in pressure. In this case, it will read in a difference from 0 to 10 psi. It gives us out a voltage from 0 to 5 volts, and we've assumed that this is a linear system, meaning the slope of our line follows y equals mx plus b. And this is going to be really important for this discussion, so I'm going to write it over here. I'm going to use the same color as our line here. I'm going to say y equals mx plus b. And what we've determined is that this goes from 5 volts at our maximum, so we go from 0 to 5 volts. We have a span of 5 volts, and we have an input span from 0 to 10 psi, or 10 psi. And our slope, whenever we say slope, we should think sensitivity. So this is the sensitivity of our measurement system. We also said that we have b, which is a null. This is our null value, so our y-intercept. In this case, it is just 0. I'm going to rewrite this really quick for us, so I'll erase this right here, and I'm going to rewrite this as the actual equation. And 5 over 10 is 1/2 x plus b, and b again is just 0, so we can just get rid of that, and this is what we have. Now let's say we send out one of our engineers, somebody working for us or with us, down to the line to pick up one of these sensors off the shelf and to measure its output based on an input response. So they give this thing some differential pressure and they measure the voltage coming out. And I'm gonna exaggerate this really quick, but maybe we get an output. They take a whole bunch of data points and they get an output that looks like this. Well, first thing that we can immediately notice is that for our new line, our test data, our test line, we have a different slope. I'm going to write this over here. Our new line, our test line, has a new equation for it. And in this case, again, it's still linear, so it's still y equals mx plus b. But let's just assume that this lands somewhere out here at we'll say about 6, a pressure value of 6. So for our new line, we have y equals 5/6. And you will notice that this hasn't changed our span or our range. So we have an input range that is still 0 to 10. So we still have the same range. Our input range hasn't changed. That is still 0 to 10 psi. Our input span hasn't changed. Our span is still 10 psi on our input. So our range and span haven't changed, but we are no longer at those minimums and maximums. Oops, let's see. I want to go back and grab my right color here. We're no longer at those maximums and minimums. So I'm just going to drop a line down, and let me move some of this axis out of the way here. So we're going to say that we're at a value of 6. There we go. 6, and this is our pressure delta in psi. Great. So we are at a delta of 6 psi. Okay. This is kind of nice, but we actually have error, right? So these slopes obviously are not the same slopes for our system, and this is going to cause us a problem. And we still do have the same b, right? This b is also 0, so that hasn't changed anything. So our slope for our test data is 5/6 x. So y equals 5/6 x. And this is known as our error, our sensitivity, again, slope sensitivity error. And the way we compute this error, let me bring this up over here, is similar to the null error. So I'm going to use a small e, and I'm going to write an S since this is our sensitivity error, and that is going to be the absolute difference between our real, our ideal, our design. Let's see, here's our design, our sensitivity, that is our real design sensitivity, we'll call it SD, and our test, our sensitivity that we've tested, and this is going to be this absolute difference between these two. And we use an absolute difference because we don't know if this slope is going to be above. Maybe we send our friend back out to the line to grab another sensor to verify this again, and this time when our friend verifies the sensor, they get test data that looks like this right here, and we would have a different slope. What we want to use is the biggest absolute differences in slope. So assuming, we can visually check this pretty easily, that our teal line, this line over here, this test line over here, has our biggest difference in slope, much bigger than that for our red line. All right. Well, this is nice that we can compute this error sensitivity. We would sometimes call this over here an absolute error. And we like to express these errors as usually a percentage of our full-scale output. As a quick reminder, our full-scale output is this value up here. And in this case, that value happens to be 5 volts. The way we would write this, what we would do over here, is we would say that we have our error sensitivity, and that is going to be divided by our full-scale output, and we like to do this as a percentage, so we're going to multiply by 100, and the way we would normally write this, if we're just writing this for other people to know, is that we would have a sensitivity error at FSO equal to, and we would bring down this percentage up here, we would bring this value down, and that is our sensitivity error at full scale output. Again, this is expressed as a percentage. And we always, always, always pick the biggest difference in slope absolutely, whether it's above or below. And that's all there is to it. It is as simple as that to find our sensitivity error for any sensor.